In this video tutorial for Shape version 5, we're going to look at the basic way of the functioning of the physics module, where we set up the radiation properties of our objects using the physical renderer. We first start by setting up a sphere. We are going to make a bipolar nebula. Change the name, bipolar, and now add a squeeze modifier. This yields a bipolar structure immediately. Now for physical computations, we better make our objects the right size, physical sizes. So we go to the primitive tab and set our object to a size of 10 to the 15 meters of radius. Now, of course, our object is out of range, so we go to the render module and the image tab, where we can set our size of our image or our work range to 10 to the 15 or 1.3 to times 10 to the 15. Go back to the 3D module. Now our object is in range again. You can rotate to see the bipolar structure is not very useful at the moment, so we have to edit the squeeze modifier. And the other viewports we can get back by scrolling the zoom. Okay. The mouse wheel does this zooming. Okay, here we're back. Now we edit our squeeze modifier. And set the external points to the size of the object, which is 1 times 10 to the 15 meters. Remember that we are using meters as SI units. Okay, now rescale the plot, the graph. Now our object has a bipolar structure again. You can edit the details, of course, by editing this graph. Let's leave it as it is. Okay, now we make this a shell by setting an inner radius of the primitive object, say 0.9 times 10 to the 15. Now we have a shell structure. And we set a density that goes decreases with distance. Open the density modifier, and then the magnitude. This gets us to the quick mode, which we can use. We edit our function, set the constant term to 0, our reference distance to 1 times 10 to the 15, the size of the object, the exponent to minus, well, let's say 1.5, and a coefficient of 1. Close. And we can now first make a test render using the basic renderer. Fine. Now we do not get a PV diagram for two reasons. First, our slit is very small. It's the little point in the middle. So let's go to the group tab, select our primary group, and make the height 2.6 times 10 to the 15. Now we have our slit here, and give it a sensible width. Click on the move button and scroll your mouse to open the slit. Now re-render, and there will be still no PV diagram because we have not assigned a velocity. Get back to the 3D module, modifiers, and add a velocity modifier. And set the magnitude to something sensible. Say we again use as a reference 10 to the 15, and we want at that distance 100 kilometers per second. Okay, now re-render, and here's our PV diagram. Okay, let's set some resolution, 15 or 10 kilometers per second, and also for the image, let's say 2 times 10 to the 13. It's not enough. Say 5. Okay, here we go. Now our density looks kind of uniform. The gradient is not very strong. Scaling is linear. Okay, so let's adjust that a little bit, our density modifier. In the quick mode, let's say it should go down by with an exponent of 2. Okay, now it's more reasonable. Okay, now we want to use our physical renderer and set up a spectral line centered on, say, the oxygen 3 line at 500 angstrom. So we set the reference wavelength lambda 0 to that wavelength, and our maximum range a slight bit above that. And the lower one a little bit below. Okay, and now we set up our line and go to the physics module. Here we add a new species. We click on the add button. A add species dialog shows with it where we can select a variety of species. We're going to start with the custom one, which is the simplest one and most customizable, where you can set your own coefficients. It starts with the emission coefficient enabled. If you want absorption, also other options, you have to enable them. We're going to use an emission coefficient only at this time, and we open our editor for the emission coefficient. By default, there's a lambda or wavelength independent coefficient that is proportional to the square of the density. We are going to set up a Gaussian spectral line first, and for that we go to the templates and select Gaussian, apply, go back to the function. Now we have a Gaussian function here. We're going to eliminate the coefficient before it, so we get a normalized Gaussian function with at the position B, and with the width parameter of C, we go to the variables tab to set these values, and we're going to set the B value to our wavelength and C to a very small value, 10 to the minus 11. So the width is small enough to be resolved by our simulated spectroscopy. Okay, we can close this now. And now we go to the 3D module, select our object, make sure it's selected, then to the species tab. and here we select the custom species that we just created. If we have more species created, then they will all show in this selection dialog. And at this now we have another species shows up, which is the default species that is used when there is no manually defined species available. We delete this default species, select it and click on remove. Now we are left with the custom species. Okay, now we can try to render, make sure we have the physical render selected, yes, and see what we get. With a bit of luck we get a spectral line. We do not. We should increase the number of bands to something like 25. That is one problem, and here is a mistake in the lambda max setting. We need an E here. So, and also in the lambda 0, otherwise it doesn't recognize the number. Okay, let's try again. Okay, we get nothing again. What is going wrong? Let's look at our species. Emission coefficient. Do we have our numbers correctly filled in? Maybe they are. Is this too small? Say 3. This should be okay. Is there something missing here? Or custom species? Let's take out the temperature. We don't need that. Okay. This looks alright. Is this alright here? 10 to the... Okay, our max is smaller than our minimum. It should be the other way around. Oh no, the minimum should be smaller than our central wavelength. Okay, let's try again. Yep, now our object is there in the image and in the PV diagram, and a reasonable shape is there. Our resolution is too low, so we can increase the number of bands. And here we go, we have a quite a nice PV diagram. Now we notice that the ends, the peaks, the ends of the bipolars are much brighter than the central region, despite the fact that we have set the density as a power law with distance. This is because our species is insensitive to the density right now. We go back to the physics module and edit our emission coefficient. Since we have taken out the density dependence, we should put that back in and set this to, say, square of the density. Now we should get a different result with the brightest emission in the middle. There you go. Now we have a nice bipolar hourglass structure, which we can make more easily visible by editing the image, scaling, setting it to square root. Same in the PV diagram. Okay, maybe our resolution is a bit too large. Let's set it to 5. Oh, that shows these channels again. maybe our range is now too large. Let's increase this to 5. So, or 6. So we have 2 on either side of the central wavelength. Okay. We can now play with the orientation. There we go. In this result, there is not much difference compared to the basic rendering. This becomes interesting if we add some other physical effect like absorption. Now, let us include a torus, which will be made of dust, a dust torus, and go to the physics module to generate it at a dust species. Have it absorbing instead of emitting, and we use the custom settings. We could choose from a different, let's say, amorphous carbonyl. So, say range. Here we see the amorphous carbon absorption or absorption index, and then go back, assign this to the torus. Let's rename it to torus. Go to the species, select the dust species, add it, make sure it's really there. Okay, and now we can try to render, and we will see no effect probably. We haven't adjusted the density, right? No difference. So let's adjust the density to a value of order 100. See what we get. Now we get our absorption from the torus, which is also reflected in the, or visible in the PV diagram. So this is how you get started with the physics module, setting up a thin spectral line that will show in the PV diagram, and then add an absorbing feature such as a dust torus. Thank you very much.